Okay, I'm going to have us get back to section 2.2 here. We're talking about limits. We've introduced the idea of a limit. Now, the idea of a limit is essentially observing values of a function around a number, but not at that number. Okay. Now, one question that we might have, after seeing some examples in the previous video is, do limits always exist? Okay. I was able to set up a table here and, guess a limit. Like, am I always going to be able to do that? Or, no. Limits don't always exist. Okay. So let's take a look at some examples next here. Find the limit as x approaches 0 of the absolute value of x over x if it exists. Okay, well, I've made a graph of this function. Now, of course, x can't be 0, right? 0 is not in the domain of this function, but I don't care about that, right? I'm not interested in at all at what's happening at 0. I'm interested in what's happening around 0, okay? Let's select values that are on either side of 0 and see what the output looks like. Okay, now if x is a positive number and close to 0, although for this problem it's not going to matter, but you're close to 0, then x is positive, right? So the absolute value of x is going to be a positive, and x in the denominator is positive, right? So if you have a positive number divided by the same number, you're always going to get 1. So it's not going to matter what positive number we select, the y value will always be 1. Okay? And so I'm going to draw this horizontal line at a height of 1 here for if I'm greater than 0. Now, if we're less than 0, the absolute value of a negative is a positive, right? So you're going to have a positive divided by its opposite. Well, a positive divided by its opposite will always return negative 1. Okay? So you're going to have a horizontal line at a height of negative 1 as long as x is less than 0. Right? So for this problem, I think it kind of depends on what side of 0 you're on. Right? If you're on the right side of 0, you always get 1 as the y value. And if you're on the left side of 0, you always get negative 1. Okay? These results imply that the limit as x approaches 0 of the absolute value of x over x does not exist. Okay? In order for a limit to exist, you have to be approaching the same y value on either side of x. Now, we're going to see later the idea of one-sided limits. We'll talk about that later in this section, actually. This limit would not exist. Okay, here's another example. Find the limit as x approaches 0 of sine of 1 over x if it exists. Well, I've set up a chart here, and I've got a picture of this curve. Now, x can't be 0, right, because I know I can't divide by 0, but again, I don't care about that. I don't care what's happening at 0, I care what's happening around 0. Okay, and that's the idea of a limit. So I want to be selecting values of x that are close to 0. Now for this problem, it's going to be enough for us to get the conclusion by just looking at what's happening on the right side of 0. Although you'd be looking at what's happening on both sides there, let's just take a look at what's happening to the right of 0. So I'm going to select some values of x that are close to 0 and positive, and see what the output looks like. Now, along with that, I would also add, we'd want to select nice trig angles, ones that we don't have to run to a calculator for, okay? Or values of x that would result in nice, basic trig angles. So like, for example, if x is 2 over pi, a 2 over pi is going to be a number very close to 1, right? Pi is roughly 3.14, right? So 2 over pi would be a number that is going to be less than 2/3. 1 over 2 over pi means that you'd flip the denominator and you'd have pi over 2. Sine pi over 2 is 1. Okay, so 2 over pi is roughly around 2/3, and so you'd come up to a height of 1, plot a point. Okay, now how about if I get closer to 0, I'd want the denominator to get bigger. What if I were to use 2 divided by 3 pi? Well, 2 divided by 3 pi is going to be a smaller number than 2 over pi, right? Because the denominator is bigger there. 1 divided by 2 over 3 pi, flip the denominator, that'd be 3 pi over 2. And sine 3 pi over 2 is negative 1. Okay, so 2 divided by 3 pi, that's going to be a number that would be less than 2/9. And so 2/9 would be around here, and I'd come down to a height of negative 1 and plot a point. Okay, so what if I'm getting closer to 0? Like what if x is 2 over 5 pi? 1 divided by 2 over 5 pi is 5 pi over 2. Sine of 5 pi over 2 would be the same resulting output as sine of pi over 2, which is 1. And so 2 over 5 pi, that'd be closer to 0. You'd come up to a height of 1, plot a point. About 2 over 7 pi. Well, 1 divided by 2 over 7 pi would be 7 pi over 2. Sine of 7 pi over 2 would give me the same output as sine of 3 pi over 2, which is negative 1. And so I'd plot a point at a height of negative 1. And so you can see the other values that I've selected there. Now, in these numbers that are selected, I'm getting 1 or negative 1 each time. And what this curve is doing is it's bouncing between 1 and negative 1. And as x is getting closer and closer to 0, the oscillations are getting tighter and tighter. So this curve is going to be approaching the y-axis, but it'll never get there. The oscillations are getting tighter and tighter, but x can't be 0, right? So at no point will this graph ever cross or touch the y-axis. Okay, a similar deal would be happening if x were a negative. You're going to have this oscillation thing, and the oscillations are going to get tighter and tighter the closer that you are to 0. Okay, now for a limit to exist, you have to be approaching one y value on either side of x. Well, in this problem, I'm not approaching one y value. If the curve is just bouncing between 1 and negative 1, I'm not approaching one number. Okay, therefore, this limit does not exist. Okay. Now, there's a caution that I've stated next, which is super important. It says, using a table only allows us to guess the value of a limit. Okay, in the problems earlier in this section, and also in the last section, I was using a table. A table, quite honestly, is a poor option. Okay, and I'm going to talk more about that as we continue on with the topic of limits, but the reason why it's a poor option is because it's easy to guess wrong. Okay, and it's tough to know when to stop calculating. Like you want to be selecting values that are close to a number. What does it mean to be close to a number? Okay, like is 1 close to 0? I mean, it's kind of vague. Close on a scale of 0 to a million, sure. One's close to 0, okay, but close on a scale of 0 to 1.1? No, 1 is closer to 1.1 than it is 0. Okay, so like, what does it mean to be close? Like, how do you know when to stop selecting values of x? Is what I want you to see there. Well, to show the caution statement here, I've got another example. Find the limit as x approaches 0 of x cubed plus cosine of 5x divided by 10,000. Okay, now you can use your calculator here and type in the function. And I can quick do that here. It's x cubed plus cosine. I'd want to make sure I'm in radian mode. I believe I am. Cosine of 5x divided by 10,000. Okay, and I'll hit enter. And then I'll go to my table next. And okay, so like if x is 1, I get roughly 1. Okay, now what if I get 0.5? 0.5, okay. Well, you can see now my calculator is only going out so many digits there, but if I go over and highlight that number, I can see more digits. Okay, if I go up to 1, it's not exactly 1 for the y value, right? It's this guy here, this infinite decimal. And so I've got those resulting numbers indicated. X is getting closer and closer to 0, and I've just used the right side. It's enough to just show what's happening on the right side to make my argument. Now, from our table, it would be natural for somebody to guess that the value of this limit would be 0. Okay, like it looks like that's where the y values are headed towards. 0 would be a wrong answer, though. Okay, the correct answer is actually 1 over 10,000. 1 over 10,000 is very close to 0, right? So I mean, if the answer is very close to the number, it's easy to guess wrong. Okay, and that's a huge pitfall in guessing the value of a limit. Okay, now in the next section, we're going to develop foolproof methods for calculating limits. Like we don't want to guess our answer. We want to know for sure what the answer is. Okay, it's easy to guess wrong. So something to be really careful about. And as I mentioned earlier, a table is really a poor option for working with limits because it is so easy to guess wrong. Okay, now the only reason why I'm using tables at the moment is just to introduce the idea of a limit, but ultimately we want to break away from that habit there. I mentioned one-sided limits. Okay, now I'm going to talk about that next. There's a definition. We write the limit as x approaches a from the left, is what that minus sign is, of f of x equal L. And here's what we'd say as we read that equation. Similarly, the limit as x approaches a from the right of f of x equal L means the right-hand limit of f of x as x approaches a equals L. Okay. So the sign there in the upper right corner is just indicating what side of A you're on, if you're on the left side or the right side. Now, in an earlier example, the first one I had shown you in this video, the limit as x approaches 0 of the absolute value of x over x did not exist because it kind of depended on what side of 0 you were on, right? If I go back to that problem, like if I'm on the right side of 0, the y values are always 1. And if I'm on the left side of 0, the y values are always negative 1. And so that's what I've stated here. Okay, if I'm on the right side of 0, this limit is going to result in 1. And if I'm on the left side of 0, the y values are going to result in negative 1. Okay, now because you're not approaching the same y value on either side of 0, that's why the limit as x approaches 0 of the absolute value of x over x does not exist. But the one-sided limits do exist. Okay, like if I only care about what's happening on the right side of 0, I get 1. Okay, so that's one way to explain a limit. Okay, you have to be approaching the same y value on either side of A, is basically what I'm saying here. In this next example, I want us to consider the graph that I've got drawn, and we'll answer some questions about the graph. Okay, part A, the limit as x approaches 1 of f of x. Well, that would be 3 then, right? 1, 3 is on the graph, but which I don't care about. I care about what's happening around 1. Okay, so if I'm around 1, it looks like the y values are approaching 3 on either side of x equal 1. Part B, the limit as x approaches 3 from the left of f of x. Okay, well here's 3. If I'm on the left side of 3 and close to 3, it looks like the y values are getting closer and closer to 2. So 2 would be that answer. The limit as x approaches 3 from the right of f of x. Well, if I'm on the right side of 3, the y values are getting closer and closer to negative 2, it looks like. Okay, now the limit as x approaches 3 of f of x does not exist because it kind of depends on what side of 3 you're on, right? If you're on the left side of 3, the y values are getting closer to 2. If you're on the right side of 3, the y values are getting closer to negative 2. They're not approaching the same y value. Part E, f of 3. F of 3 is 1, right, since 3, 1 is on the graph. Another great example to show you that f of a number is different from the limit as x approaches that number of f of x. Two completely different things, right? F of 3 is 1, but the limit as x approaches 3 of f of x, that does not exist. Okay, don't get those two things confused. Some students will do that. Part F, the limit as x approaches negative 2 from the left of f of x. Well, here's negative 2. If I'm on the left side of negative 2, it looks like the y values are approaching negative 1. Okay, part G, how about if I'm on the right side of negative 2? Well, the y values are also approaching negative 1, it looks like. Okay, so the limit as x approaches negative 2 of f of x, that will exist. That's going to be negative 1, since you're approaching the same y value on either side of negative 2. F of negative 2 is negative 3. Again, note that f of negative 2 is not the same as the limit as x approaches negative 2 of f of x. Two totally different things. F of negative 4, that's undefined. Well, yeah, negative 4 is not in the domain of the function. I've got an open circle there. All right, so I'm not defined at negative 4. Okay, and we'll go ahead and stop there.